All right, welcome to the HKN ECE 10 final review. Let's get started. I know you have your final coming up. So right now we're going to review some key topics, and that's going to include topics prior to the midterm and then some key focuses after the midterm. I've taken a look at the previous finals from this professor and tried to tailor the topics a bit based on what I think you're likely to see on the final exam. Potentially a lot of steady state, some circuit simplification, a lot of initial conditions, that sort of thing. So let's get started. So pre-midterm topic review, a couple of slides on this. We're just going to briefly review some concepts that you guys should have down by now. And if you don't, this is a great time to make sure that you have that foundation. So voltage in general is defined between 2 points. Sometimes the lower point is implicit, and sometimes you're going to set a virtual ground that you defined. It's really up to you, but once you pick a definition, you have to stick with it for the rest of the problem. That's true for a lot of topics in this class, including component direction, that sort of thing. Current only flows through a closed loop. One of the things that you'll see when you try to apply initial conditions is that you'll end up with open circuits in your loop, and you have to remember that you're going to have no current in that case. Now, power in watts, direction really matters here. So make sure that any answers that you get make sense with the physical reality of the system. For example, if you have a current source or a voltage source, you should be getting a positive number because it should be producing power, not absorbing it. Now, again, just in general, you should know how resistors, inductors, and capacitors behave in series and parallel, what their voltage current relation equations are, and what their relationship to power and energy in this class is. Now, it's important to note that Kirchhoff's laws apply in all of the domains that you use in this class. So they're going to apply in the time domain and the frequency domain. So it's really important that you have a good handle on them. Now, Thevenin and Norton equivalence, that's when you transform a black box circuit into either a voltage source and a load resistor, or a current source and a load resistor in parallel. So you're going to want to know how to do that. And it's part of one of the examples that we're going to do. We're going to do it in terms of impedances and sinusoidal steady state. But this is, again, a pre-midterm topic, so make sure that you understand it because it's very foundational to what the rest of this class builds on. Now, circuit responses, it's important to understand some terminology. There's a lot of different states, but these are the two most important and fundamental for you to know. So the first is the zero state. So all initial conditions are zero, but you have an input, and you're just looking at how that circuit responds to the input if you had no energy storage or anything leading up to it. Now, the zero input is when you have initial conditions, like you have a capacitor or an inductor with energy stored across them. And so you're going to look at how, when the circuit is closed, how that capacitor discharges and affects the other elements of the circuit. So it's going to act as like a source until it's discharged past a certain point. And then if you have an RLC circuit, you're going to get some oscillation between the two energy storing components. Now, the complete response is the sum of the zero state and the zero input. It's important to note that we're assuming a linear circuit here. The vast majority of the circuits that you deal in this class will be linear, but that's an important thing to note, that this piece of the analysis won't necessarily translate well to other classes where you're going to be looking at circuits which are more complicated and potentially nonlinear. So initial conditions, it looks like Professor Pamarti is very fond of circuits with several switches in them and a lot of components, so initial conditions are absolutely critical for you to understand. So we look at the circuit before the switch is flipped. I recommend redrawing the circuit in this case. It can be really helpful to understand what components you have to pay attention to and what you can ignore if you're looking at before and after a switch flip. So in the long time or steady state case, inductors go to a wire or a short circuit, and capacitors go to an open circuit, and you're going to be able to apply this long-time steady state relationship to be able to determine what is going on with the rest of the circuit, like is there current flowing through the circuit. So most of the cases you're going to be looking at a circuit with no impulse response. And so you're going to essentially have these two conditions, and they're going to be true for the vast majority of the circuits. However, if you do have an impulse response, these are not going to be true, and you're going to have to integrate from 0 minus to 0 plus. So for example, for the capacitor voltage, you would say VC at 0 plus equals 1 over C. And then the delta in general can have some constant attached to it, but this would be your infinite current going through the capacitor loop. And then you have to remember to add this term here to make sure that you're using the definition of the derivative properly, and making sure that you're accounting for any energy stored across the capacitor before the infinite current. Now, LTI systems, so most circuits that you're going to be dealing with are linear in time invariant, and if you've taken 102, you potentially have more background in what you can do with LTI systems. EE10 kind of glosses over the exact mechanics of the Fourier transform, and this is a tool that can be very useful in this class if you know how to do it. If you don't know how to do it, you can still do perfectly fine, but you're going to have to rely a little bit more on your intuition when it comes to the circuit itself, as opposed to your ability to just solve the differential equation and not really need to figure out what the initial conditions are. So if you do know the Fourier transform, you can just take the Fourier transform of the differential equation, find the solution, and just have the complete solution, and then you can just take derivatives and figure out what the initial conditions were from the solution. That's a useful strategy if you know how to do that. If you don't know how to do that, you're going to be using the LTI systems to find the complete response by convolution with the impulse response. So typically when you have, let's say you have an output y of t to a circuit, and you're looking to find the impulse response. So you're going to have some sort of impulse, which is going to take the form of like k delta of t, where k is a constant, and then you're going to convolve it with, sorry, x of t is going to be your impulse, and then h of t is going to be determined by the relationships within your circuit. And once you find this transfer function, it's also called the network function in circuits. So that would be the Fourier transform of the impulse response. So that's going to be the h of j omega in the frequency domain. So once you have this information, you can use it to arbitrarily find any responses to any potential inputs that you have. So if you are not super strong on the Fourier transform, because I know that 102 is technically not a prerequisite for EE10, but a lot of people take it concurrently. So what you're going to have to do in this case is you're going to have to, it's most important for you to know the Fourier transform of the delta function and the Fourier transform of the cosine function. So you can just Google that in a Fourier transform table and then just apply that to your functions. Essentially, that's what you have to know, and you have to know that convolution turns into multiplication. But if you don't know anything besides that, then you're basically going to have to rely on your intuition when it comes to the circuit and the various initial conditions that pop up as a result of that. So please feel free to stop me and let me know if you have any questions. So our next big topic, and this is really important for you to have a great understanding of, because this is the focus of at least a lot of previous problems on your professor's finals. So sinusoidal steady state, it's a circuit solving technique when you're interested in the steady state response. So that means that when you apply this technique, the circuit must be LTI. The input must be a sinusoidal input or toned, so that's going to be a sine or a cosine wave. And you're not going to be able to figure out any information about the transient behavior from this technique. So it's going to be important that you don't really care about what happens to the transient. And so the main thing that you have to do in this case is you have to transform everything into its phasor representation. So again, this is essentially the Fourier transform, but what we're doing is we're taking out, basically, we're looking at the time domain components being separate from their frequency domain components. So if we use Euler's formula and we rewrite cosine of omega t plus phi, and then we factor out e to the j phi, then we'll be able to represent this in the phasor domain. So it's important that you know what sine and cosine look like in the phasor domain. So remember, sine is cosine of omega t plus pi over 2. And so you're going to end up with a negative sign if you have a sine component here. So then what you're going to do is you're going to represent all of the given differential equations or differential equations that you find as a result of applying the current voltage relationships across the various components in the circuit. So for example, if you end up with like d squared vt dt plus so if you end up with a differential equation like this, you're going to want to move it into the phasor domain or frequency domain. So you're going to want to write it in a form like this. And so the derivatives become the j omega terms. And then everything now, instead of like here it was in the time domain, but here it's going to be a function of omega instead of t. So conventionally, we write the variable terms in the frequency domain as capital letters and in the time domain as lowercase letters. So if you see your professor's notation in that respect, that's just a hint for you to tell what's going on in the problem and what sorts of things you're going to try to find as a result. So another important topic in this class is impedance and admittance. So impedance and admittance is essentially trying to find a linear relation between the voltage and current across all of the components. So when you have Ohm's law V equals IR, that's a linear relationship. It doesn't have any derivatives. It's very easy to deal with. And so we would like to have linear relationships like that for the inductor and capacitor because they have derivatives with respect to time in them, and those can make the equations a lot more complicated. So it's important to us when we're trying to do analysis that we come up with a simple set of equations that are easy for us to solve. So the way that we do that is with impedances and admittances. So we're essentially trying to find Ohm's law for inductors and capacitors. So all we do is we take V equals L di dt, and then we take the Fourier transform of it, and so the j omega comes down, and then looking at this equation, we can say that if z is replacing r, then z in this equation is j omega L, and we can do the same thing with capacitance and get a 1 over j omega c. So it's important to note that when you introduce a j term into the conductance, you're going to have a lead or lag in your current voltage. So if you have V of t equals L di dt, and then you transform this into the phasor domain and you get V equals j omega L I. So what you're going to see here when you represent this as its phasor form, like let's say that V and I are both cosines, so that you have A e to the j phi and j omega L times V e to the j phi. And let's assume for sake of argument that these have the same phase. So when you multiply a j here, you can do a substitution and essentially get and then what you can do is when exponents multiply, they add, so you're going to get like omega lb e to the j of like phase 90. And then when you transform it back to the time domain by taking the real part of a e to the j phi e to the j omega t for the left-hand side, and then the real part of omega lb e to the j phi plus 90 times e to the j omega t for the right-hand side. So when you do this transformation, you're going to get, for example, let's say our input was a cosine, you're going to have a cosine of omega t plus phi equals, and then this is going to be a sine term here. And so you're going to get and then if you, for example, draw these two, you're going to have the cosine, it's going to look something like this. And then you're going to have the sine is going to look something like that. And so if you look at where these are at various points, you're going to see that these sine is 90 degrees ahead. And so that's going to form your basis for the lead and lag. And it's important to note that impedances behave like resistors, so it's going to have the same series and parallel behavior that you're probably most familiar with. And KVL and KCL still apply. So just some brief terminology. I didn't really see this emphasized in your professor's final exams, but it's important for you to know. The real part of Y is conductance, and Y is the admittance, which is 1 over Z. So make sure you be careful when you have like the imaginary term on the bottom of your denominators. You're probably going to want to rationalize that. So complex power, this is essentially a crutch, a mathematical crutch. It doesn't exactly exist in like the real world, and it's just a way that we can represent a circuit. So for example, if we have 2 black boxes and let's say that this is our source and this is our load, and let's say in here we have, I'm just going to use for sake of argument the Thevenin equivalent for both of them, but as you know, you can transform anything into the Thevenin or the Norton equivalents. So this would be our source resistor, this would be our load resistor, and then you have V source and V load. So essentially what complex power is it's the power connecting these 2 black boxes. So it's going to be the power that goes across here. And so you should be able to apply the P equals IEV formula and figure out the power across that resistor. However, it's going to be more complicated as you're dealing with like AC inputs. Like I've drawn it here for a DC input. That's not too difficult to deal with because it's constant voltage. But as you go to tone like a cosine or a sine, it's not going to work as well, and you're going to have to deal with phases. And that's when we get complex power. And so complex power is given by this equation here. And you're going to be able to find the average power by taking the real part of that. And again, the complex power here, the real part is the only part that like actually exists. And so again, this is like, it doesn't actually, like complex power doesn't actually exist, but we use it as a tool for analysis. And so when we want to maximize power across the load, that's a very common question. We want to have what's called conjugate matching. And so we want to have the real part equal to conjugate. And so remember, when you have like A plus JB is a complex number, the conjugate is going to be A minus JB. And so you're going to want these two to match. And so if we can just see from these two equations that if the two conjugates are equal, the only number that that is true for is if B is 0. And so you're going to want to have purely real impedances. So that means a resistor, you're not going to find like a capacitor or an inductor. So if you're answering a question to find the maximum power across the load and you're getting a complex number or an imaginary number, you may want to check your work because you should be getting a resistor for if you're going to maximize the power across it. Now, the maximum power absorbed for the load is also called the available power. This is the equation for it, and your professor probably did the derivation for this in class, but this is an important equation for you to be able to know and apply. Now, quality factor is an important concept when it comes to RLC circuits. It's typically not emphasized that much in this class, but it will be in future classes. So essentially, it's how good your RLC circuit is at translating the energy between its various components. So how much energy transfers in the oscillation between the inductor and the capacitor. So you can look at this in 3 different domains. You can look at it in the time domain, the frequency domain, and the energy domain. And the quality factor does have a meaningful physical value in each of those domains. So this is a very important parameter, but I'm not going to talk too much about it because I did not see it on any of your previous exams. So now we're going to do some examples, and these examples have been pulled from previous finals, and since they sort of like combine all the concepts, I thought it would be useful to do a brief overview of the concepts and then go into the examples. So I'm going to give you a few minutes to work on those and just pause the recording. All right, so we're going to go through this problem and look at the different steps for the different parts of it. So the first part is to find the Thevenin equivalent to the left of AB. So you'll notice that you have a capacitor and an inductor, and that means that you're going to be finding the steady state equivalence. So we see that our circuit is in steady state, and so it's a linear circuit, and so we can apply the sinusoidal steady state approximations. And so what we do is we start with that. So let's redraw our circuit in terms of the sinusoidal steady state. And so for VS, we're going to ignore for this part because when you typically find the Thevenin equivalent, you're not counting on the voltage sources in the beginning. So let's redraw our circuit. And I'm using boxes to represent the impedances. So we have a resistor here, so that's going to be Z equals R equals 1. And then we're going to have ZL here and ZC here. And so ZL we know is J omega L, and we see that L is 1 Henry, so this is equal to J omega times 1. And then we have 1 over J omega C for the capacitor. And we see that the capacitor is 4 farads, and so we get 1 over J omega times 4. Now we have to find omega. So this is going to come from our source equation. So we see that this is of the form a cosine of omega t plus phi. And so just by inspection, we can see that omega is 1 and phi is 0. So that means that this equals j, and this equals negative 1 fourth j. Remember, 1 over j is negative j. So notice that these two impedances are purely imaginary. So this is something that you're going to want to be cognizant of when you do your exam. Are you just getting purely imaginary impedances for the inductor and capacitor and purely real impedances for the resistor? Easy way to check your work and figure out where you went wrong. And so the next thing that we're going to do is we're going to find the equivalent impedance for the circuit. So we see that this component is in series with these two parallel components, so we're just going to add it on. Now, this is just some algebra, so I'm gonna skip a couple of steps, but it's just rationalizing the denominator and making these two have the same denominator so that you can add them together. So you should get something, we'll just do a couple of intermediate steps so that it's easier for you to check your work. This right here is just rationalizing the denominator. And then you should get 1/2 plus j over 4. Now we're going to look at, we found the equivalent resistance or impedance in this case because we're dealing with sinusoidal steady state, and now we have to find the open circuit voltage. So let's redraw our circuit again. And this time the voltage source that we have in our circuit is going to matter because when we found the equivalent impedance, we were zeroing out our voltage sources, but now we're not. And so we're going to apply open circuit voltage across this terminal and see what we get. So we know that current only flows through a closed loop. So this part here isn't going to be consequence. So because the circuit is open, and so you're going to get voltage flowing around this loop, current flowing around this loop, but the current's not going to go over here because it doesn't have anywhere to go. So this here is a voltage divider. And the voltage across this component is going to be the open circuit voltage. And so you should remember your voltage divider equation is the voltage across it divided by sum. And then your voltage here is 4 because remember we're looking at the sinusoidal steady state, so this becomes 4 e to the j 0, and so that becomes 4. So you should get 2j plus 2. Sorry, plus 2. Okay, so now we have the open circuit voltage and the equivalent impedance, so we're going to look at the Thevenin equivalent. And so notice that the problem didn't specify Thevenin equivalent in the frequency domain or Thevenin equivalent in the time domain. So it's better to just be safe and write both because that means there's no way that you can lose points because both answers are there. So this is going to be a 2j plus 2 voltage source, just the open circuit voltage, and then this is going to be the source that we found. And then if we want to put it in the time domain, so this is the now if we want to put it in the time domain, we're going to have our voltage source. And then when we look at our complex total impedance, we're going to see that we have a real part, so that's going to be a resistor. And then this is a positive imaginary part, and positive imaginary part is inductor, negative imaginary is capacitor. So we're going to have a resistor and an inductor. And then that's going to be our Thevenin equivalent. So we want to figure out, we can easily see that the resistor is 1/2, and that this is 1/4. So now we have to find our voltage source. So the way that we do that is we look at the information that we have. So we see that we want to translate our open circuit voltage into a voltage source. And so that's going to be just transformation from the phasor domain to the time domain. And so we're going to take this so remember that this is phi, it's going to be inverse tangent and in this class our default is the cosine, not the sine. And so when we find the 2√2 this is going to be so that's how you find the Thevenin equivalent voltage from the input source. Now for part B, let's see, what are we doing? Okay. We are using the Thevenin equivalent and finding the load current, assuming that we know the load resistor. So this means that we have U plus 2J as our source, and then it's going to go through the total impedance that we found in the previous part of the question. And then it is going to go through our load resistor, and capacitor, because we have this capacitor here and this load resistor. And similar to the previous part of the question, we can just find capacitance and note that this is negative, so we know that it's a capacitive impedance. So let's find equivalent impedance. So we have 1/4 J plus 1/2 plus 3/2 minus 1/4 J plus 2. Okay, so these are just in series, so we add them up. And then we essentially use the impedance version of Ohm's law, so instead of V equals IR, it's V equals IC. Now this is our capacitor current through the load impedance. So this is what we're looking for, but it is not in the time domain. And so we want to make sure that we provide that answer because the question right here said that we want to find IL of t, and that's the same as IC of t because you have a single loop. So always make sure to read the question and remember to find the quantity in the right domain that you're looking for. Now this is the general conversion formula back to time domain. So we're just taking magnitude and the phase. So this would be our current in the time domain. Now part C. Part C, we are finding the value of the load resistor such that the maximum power is delivered to the load impedance. This is our Thevenin equivalent here. And then this is the load impedance that we found that was given to us, sorry. And so we're going to use the complex power here. And we're going to find power across the load. So this is going to be times L conjugate. And then this right here is voltage divider. And so we're going to do CL over CL plus CS times the, where this is the source here. And this is just V equals IZ, just finding the current and then taking the conjugate of that. That's what this star here means. So if we do that, we get so this is going to be our complex power, but remember this doesn't actually exist in the real world, so we're going to want to find the average power in this case. And that's going to be the real part of this. And remember that these are finding magnitude, and magnitude comes out as a real quantity, and so we're essentially just finding the real part of this. And so we get this equation here. So what this notation here is saying is that you have the resistive part and the imaginary part of the impedances. And so we can control these parameters. And so we do conjugate matching and we set XL equals negative XS. And so this part goes to 0. This conjugate matching strategy is something that you should have derived in class, but if you didn't, just make sure you remember that if you want to maximize power, you need to make the denominator smaller, and the way that you do that is you match the conjugates. And then you take a derivative of this expression with respect to RL, and if you set it equal to 0, you will eventually get that RS equals RL equals 1/2 ohm. We're running a little short on time, so I'm going to be skipping some algebraic steps, but I'll just write back. Okay, so then for part D of this question, we want to find the maximum average power, and so that's going to be just the expression on the previous part of the slides that you should have derived in class. So you just plug in the numbers to that. And always make sure that you have units with your expressions. So that's the end of this example. So this example covered a large variety of topics and is a very typical question. You are likely to see something similar to this on your exam. So make sure that you know how to do the Thevenin, the impedance, and sinusoidal steady state part of it. You may or may not see the complex power, but that's more up to the discretion of your professor. So now for our next example, this was taken directly from previous example of this class. I'm just gonna go ahead and walk through it since we're running a little short on time. So for A, we're trying to find the V1 and V2 of T just before T equals 0. So I'm going to redraw the circuit with the switches in that orientation so that I don't have to pay attention to as many components. And remember, in the steady state, capacitors go to an open circuit. So that's just what I'm drawing here. So this is going to be V2, this is going to be V1, and notice that these circuits are open, so you're not gonna have any current, so we can just ignore the resistors, and so we get two open circuits in parallel, and we know that the voltage across parallel components is the same, and it's given to us that VB is 4 volts right here, and so we can just say that V1 of T less than 0. Actually, it'd be better to write this as 2 0 minus because we don't actually know that. Okay, so that's all you had to do for part A. Just realize that key realization, there's no current flowing here, so the resistors aren't going to do anything. Now, just after T equals 0, we have a very different circuit. The switches have moved. So you have a connection here and a connection here. So we're going to redraw the circuit for this case. And so we're going to have VST being part of the circuit. And since we're looking at VST at T equals 0 plus, for a cosine function, that doesn't change very quickly. And so VST is just 4 cosine at 2.5T. So we can just plug in 0. The only function that's really going to have a difference between like 0 plus, 0, and 0 minus is the delta function. So you can just plug in 0 for all the other functions. So we see that for 0 plus, this is just 4 volt source, and it's not going to be an AC source in this case. And so now what we're going to do is we have our initial conditions of 4 volts here. This is our load resistor, and this is R. And then let's just mark where the currents are. So this is going to be I1, and then the current through this resistor, this is going to be I2. Okay, so now we use the initial condition for the capacitor because there's no impulse current, so it's just going to be V equals 0 minus 0 plus equals 4 volts. And so we just apply a quick KVL to this. We see that this is plus 4 volts, plus 4 volts, plus 4 volts. And so we're going around and we need to have some of the voltages around this equation set to 0. And so note, based on the definition of our current, we're going to have a current look like that conventionally within our smaller mesh. And so we're going to have a negative 8 volts here to make the KVL work. And then we're going to, that's going to be our voltage there. And so then what we're going to do is we have our voltage and our current. We have our voltage and our resistance through this resistor. So that means that I1 is just going to be 8 over R equals 0.04 amps. And then similarly for the smaller mesh, you're going to get I2 equals 4 over, oops. 0.01 amps. And then part C. Part C, you're supposed to use I of t and I2 as your unknowns and write down the time domain mesh equations for the circuit, but note that you're not necessarily going to solve them. So we just begin writing our mesh equations. Using Kirchhoff's voltage law. And then we begin substituting in some values. These are just read off the circuit using like voltage and current relations for the different components. So if you don't know how to do that, you should definitely review your notes in that point. Now for part D, we're supposed to find dv2 dt, t equals 0 plus. So here we're going to use the capacitor to our advantage because we know that I equals dv2 dt. So therefore we can say v2 dt and then we know that I of C2 is I1 minus I2 based on the conventional current direction we chose. You can always choose a different direction of conventional current. You just have to make sure that you're consistent throughout the entire problem. Okay, and then a common question is for professor to ask you to find some higher derivatives. So let's just do one higher derivative as an example. Actually, we're almost out of time, so I'm just going to let you know the steps to do it, and then you can do it on your own as an exercise. So what you would have to do in this case is find the, this is going to be the steady state voltage. And this is going to be the steady state current. And so in order to get time domain expressions of those, you're going to have to follow the Thevenin equivalent practice that we used in the previous example to be able to find expressions for those and then take the derivatives of those expressions that you find. So I think that's it for today. That was helpful.